Hello! We're going to be talking about benzene and aromaticity in this chapter. This is kind of fun. Um, Benzene is incredibly important. It's incredibly stable, and it was the subject of some pretty fierce debate within the scientific community in the 1800s and early 1900s. But eventually they did figure out the structure. But it's in a lot of molecules that we see every day. So things like, so this is the structure of benzene. We'll talk about the structure in a minute. So benzaldehyde. So this is usually for yeah, is a flavoring for it's an artificial flavoring for almonds or I don't know, it's artificial, yeah. Or cherry. So wintergreen, methyl cloves, cinnamon, oil of cinnamon, formaldehyde, vanilla, aspirin. It's got this general structure. So it's in a lot of molecules that we use. Now, the naming of compounds. Okay, so we'll talk about naming of benzenes. Okay, the first thing you have to do is you have to take a look at if we have what are called base structures. Okay, and so these are the bases, right? Toluene only has one methyl group. Okay, we'll talk about if it's two. But phenol has an OH. Aniline has has a amine group. Benzene sulfonic acid has a sulfonic acid. Benzoic acid, carboxylic acid, acetophenone it's a methyl ketone. Okay, so it has NaCH3 here, and then anisols and a methoxy, so O methyl. Okay? So the first thing you're going to want to do is to say, okay, look at the structure. Does it have a base structure? And if it does, okay, that actually makes it a little simpler. Okay, because the name of the base structure is going to be the main chain. Okay, stuff like that. So you use the same priority rules for that. Okay, now if you have more than one, okay, there are some priorities. If you had something and toluene, something and two different groups, the toluene's going to lose. Okay, so that's just what they decided. Okay? There are other priority rules for how you get it beyond that. I believe it's dealing with reactivity and the number of pi bonds, things like that. I don't have them off the top of my head, but it gets a little complicated fast, stuff like that. But know that everything beats up the toluene. Okay. Now you're going to name the side chains. Now you don't have, if you had toluene, you don't have to put that methyl because we're already naming it as the toluene. Okay. Stuff like that. Now with a base structure, whatever the base structure is, that where that group is hanging off. So if you had a phenol, right? The carbon that has the OH attached, that's going to be automatically number one. Okay, and then you go clockwise, counterclockwise, and then you get the lowest number set. Okay, so you know where number one is, so it actually works out pretty well. And then you construct it as normal, stuff like that. So with the alkyl side chains out front, stuff like that with their numbers out in front of there to designate it. The attachment numbers out front, whatever, put them in alphabetical order. Right. Remember the di, tri, tetra, the numbering type prefixes don't count towards the alphabetical, but the other types, the cyclos, the isos, things like that, those do. Stuff like that. So, and then you put the base structure name at the end. Right? Now, if there's not a base structure, then the main chain is just the benzene. Okay? So, by that, and then you name the side chains and determine the attachment points. And now, the nice thing about this is it gets a little more complicated because every side chain is going to have a chance to be number one. Okay, and so so everyone's going to be one, and then you go, okay, do I need to go clockwise, counterclockwise? You go counterclockwise or clockwise. You go towards the nearest neighbor, and then keep going around. Okay, for the numbers, stuff like that. And so put the construct name, and then you construct it as normal, and then put benzene at the end. Okay, so if we have this one here, so chlorine, bromine. Okay, so for this one, right, there's no base structure. Right, so right. Notice how there's no halides. There's no nitro group. That's another one. If you have a nitro group on there, it's just that doesn't have priority for a base structure. Neither do the halides. So for this one, it's just going to be benzene. So like that, and so benzene. Okay, and so we have this group and that group, right? So we have chloro, bromo. Okay, so now we don't have a base structure, so everybody gets a chance to be number 1. Okay, so we're going to say, okay, so let's say this is number 1. And so if we go clockwise, we can get to a neighbor quicker. So we're going to go 1, 2, 3, 4, 5, 6, as opposed to going counterclockwise. So it becomes 1, 3. Okay. Now, if we said, okay, bromines first. Okay, now we're going to want to go counterclockwise because we can get to a neighbor quicker that way. So 1, 2, 3, 4, 5, 6. So it becomes 1, 3. So we add them up. Okay, 4, 4, and there's no way to break the tie. Okay, so if we had another one that was added up to 3, and we would this one. Right now we don't, stuff like that. And so what the chemistry gods have decreed is that when this happens, and there's no other way to break the tie, what we do is we say, okay, the first alphabetically is going to be number 1, stuff like that. So it's going to get the lowest number. So for this one, bromo comes with 4 chloro, so we're going to use these numbers here. So it becomes 1 bromo, 3 chloro, benzene. Now for this one, okay. So our base structure is actually this one here. So this is toluene. Right? That takes into account the methyl group here. So with that, and so the other side chains we have are 3 nitro groups, so nitro, nitro, nitro. Again, notice I didn't put a methyl group here because that's assumed in the toluene. It's the only way we can have a toluene. Okay? And so we know that this is number 1. Right? So 1, and so well, you got to go clockwise, counterclockwise. So just go ahead and do it when we have a base structure. It's just easy to have it to get into. So 1, 2, 3, 4, 5, 4, 5, 6. Okay, so it's going to be 2, 4, 6. Okay, so if instead we start this 1, but then go counterclockwise, 1, 2, 3, 4, 5, 6. Again, it's going to be 2, 4, 6. We add them up. 12 versus 12, and you say, oh, first alphabetically, but it turns out that it doesn't really matter which one you choose because they're both going to give the same name. Okay, so it's going to end up being 2, 4, 6 tri nitro toluene. Also, typically known by its acronym TNT, tri nitro toluene. Okay, so for this one. So, right, so here we actually have 2 base structures. We have this one, which is phenol, and then we also have this one, which is toluene. Okay. Now we have to do the priority. Everything's going to be a higher priority than toluene, so we're going to get rid of this one. Okay, so it's going to be phenol. Okay. So that makes the methyl group our side chain. Okay. And so with that, and so to do for this one, 1, 2, 3, 4, 5, 6. Right, so 4. But if we go counterclockwise, 1, 2, 3, 4, 5, 6. So that would again be 4. So it's going to end up being 4 methyl phenol. Okay. Now, if instead what we had is say, I don't know. Let's do this one. Okay. Again, we're going to have 2 resonance structures. One that's going to be right here. Right? That's acetophenone. And then this one here, which is toluene. Right? But everything's higher priority than toluene, so we're going to get rid of that. So we end up having the methyl. So So this methyl reverts to just a regular, the CH3 just reverts to a regular methyl. And we have a chloro. Okay. So we know that this is number 1, right? So we got to go clockwise and counterclockwise. So clockwise would be 1, 2, 3, 4, 5, 6. So the methyl is at 2, chloro is at 3. Okay. If instead we went counterclockwise with 1, 2, 3, 4, 5, 6. Okay, so it ends up being 5, 6. Okay, so 5 versus 11. We're going to use those numbers there. And so, right, but chloro ends up being first alphabetically. So we're going to do 3 chloro, 2 methyl, acetophenone. There you go. Okay. Now, a couple other things, little historical quirks. Okay, so if you have just a regular benzene on here, you would think it would be benzyl, right? Because how do we make a side chain, right? So if we had CH2, CH3, right, 2 carbons long, that's normally ethane. What do? Well, we take off the suffix and add ly, right? That becomes ethyl. Right? So if we had this as a side chain, right, it's benzene. Right? Well, you take off the suffix and add ly, so you would think it'd be benzyl. Well, it's not. It's not. It turns out benzyl actually has a CH2 in between the main chain and the benzene. It's a historical quirk from when they were originally studying these. They were looking at soot from the leftover from gas lights in London, and when they were looking at these, they actually had this toluene type thing, but they didn't have quite the detection capability now, and so they named it benzyl. Okay, when in fact it had this in there that they couldn't detect. And when they finally figured it out, well, they decided not to change the name, and so they kept this benzyl and said they needed a different name for when it was actually just a regular benzene side chain, and so they called that phenyl. Not to be confused with phenol, but it's phenyl. So, okay. Now, for the naming, an alternate way, and this is actually going to be kind of important in chapter 15. So that relative to whatever group you're doing. Now, this only happens if you have 2 groups attached to the benzene. Okay, it's kind of like cis and trans, right? You can only have to do that when you have 2 groups hanging off the double bond. Okay, if you have more than 2, then you can't do this. Okay, you just do the number. And so relative to whatever you're naming, 1 away is ortho, 2 away is meta, and across is para. Okay, so here is ortho-dichlorobenzene. Here it's meta-dimethylbenzene, or actually it's metaxylene. We'll talk about that next slide. Stuff like that. Or here, right, this is the priority, so it's going to be para-chlorobenzaldehyde. Okay? Stuff like that. So this only happens with 2 groups, stuff like that. I would stick with the numbers. I think it's a little bit better, but we'll see this. If you see this, you'll know. And you do need to start thinking about orthomet, knowing about these because it becomes important in chapter 15. Okay. Xylenes are the special case where it's dimethylbenzene. Okay, and you'll have orthoxylene, metaxylene, paraxylene. Okay. No other groups are present. If not, it becomes a dimethyl. Something like that. And so, with some exceptions, something like that. But it's pretty much just dimethylbenzene, something like that, so it's called a xylene. Something like that. So, we'll talk about that later, about when this is actually an incredibly important molecule in your daily life, probably. Something like that, we'll talk about that in a minute. Okay, so one of the things that happens with benzene is that it is significantly less reactive than just a regular alkene, okay? So remember, benzene has this general structure, right? Here, right? So if you had, if you just had cycloalkene, right, and you threw bromine on it, right, you're going to get bromination, right? Br, Br. If you do that same reaction, just throwing bromine in there, it's not going to do it. No reaction. They're just going to sit there and wave at each other. Okay, same thing with camphor acid. This can work, the hydrogenation can work, but you're going to have to, it's going to be slow, and you're going to have to crank up the temperature and pressure, which is exactly what you want to do with hydrogen, stuff like that. So it takes a lot of pressure to be able to do that. And so why is, right, so the only way that you can do this is actually, do this reaction is if you do, actually have to put in a catalyst, an acid catalyst, a Lewis acid catalyst, and even then it's kind of slow with that. So, and not only that, you don't get the addition. You actually get a substitution, because what you want to do is you want to reintroduce the benzene. Here, when you do the addition, right, you've broken up the benzene, right? So it's not double, single, double, and then single, 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 right? So you've broken that up. It doesn't want to do that. So that once it gets the benzene back, because of that stability. Okay? So with that, so just as a reminder for these are not two different. These are the same molecule. Okay, so with that, so they're just different resonance structures of the same molecule. Okay, so notice how the double bond is here and it's not there. It's been shifted over one. These are equivalent structures. Okay, and you'll see me switch between the two, and it really does not matter. Okay, it's not an equilibrium; it's a resonance structure. Okay? So those just kind of flew out of my head. Okay. The resonance hybrid, okay, is, remember, having all of these as a sort of 1.5 bond. And so this is, you'll see this sometimes. You'll see me draw this sometimes. You see this drawing. We saw that earlier in the first slide. Okay, this is just indicating the resonance hybrid. This is technically what's happening. But lots of times when you're actually doing chemistry, you want to have the double bonds shown because it makes it a little easier to see. But if you're just drawing a structure and you don't worry about, and it doesn't really matter, you can just put the circle in there to indicate it. Now, the structure of it is actually, remember, it's just like with the conjugate, it's a conjugated system where each of these carbons are going to have a pi bond, okay? And so, because they're like this, right, they're going to smear together, okay? And the easiest way, the best way I've been able to describe it is you take a burger, okay, hamburger, and then instead of the buns, right, you got Krispy Kremes, donuts, okay, stuff like that. And so you have p orbitals on the top, p orbitals at the bottom, right? That's your donut. And then the carbon in the middle is going to be the burger, okay? So with that, and so that's sort of what it looks like. Okay? If you do the quantum mechanics of it, that's exactly what it predicts, right? So there's a lot of electron density in the middle, radiating it out, and there's no actual double single, right? It's all sort of smeared together. Okay? So this characteristic of being like benzene, where you have this extra stability, is called aromaticity. Okay, and if we think of it, when we initially think about things that are aromatic, right, we think of things that smell good. Okay, that's why they originally looked at this, because a lot of these smelled really good, and so they just kept the name aromatic. If it behaves like benzene, okay, we call that aromatic. If it doesn't, it's either non-aromatic or anti-aromatic, and there's a little slight difference between the two. Okay, the chemistry is going to behave more like alkene type chemistry. Okay. Like that. And so, is it aromatic? Okay, so it has to be in a ring. Okay, so the molecule has to be a ring. Okay, now does every atom in that ring, around the ring, not including the hydrogen, does it have an available pi bond or a p orbital? Okay, and the way that you do that is if say there's part of a pi bond, a lone pair, and/or a charge. There's some exceptions for this, for the charge, but pretty much. Okay, the structure needs to be flat. It needs to be sp2 hybrid, so that it's flat, and so all of those p orbitals can align. Okay, if it's not flat, it's kinked. Those p orbitals can't align. It's going to make it anti-aromatic. Okay, and it has to contain the correct number of electrons in the p orbitals. These are what are called the Huckel numbers. Okay, and it turns out that you go 2, 4, 6, 8, back and forth, back and forth. I usually just think about this chart, and I can. Because I know benzene is aromatic. Okay, so I have sort of a flagpole. I know 6 pi electrons, right? 2, 4, 6. Okay, right? 2 from here, 2 from here, 2 from here, 6. I know that is aromatic. Okay, so with that, so I can go bounce back and forth. 2, 4, 6, 8, 10, 12, 14, 16. Aromatic anti, right? But that's so for here, right, we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Well, that's anti-aromatic. Okay. Now, you can also figure out this if n equals 0, it's 2, n equals 1, if that's 4, n plus 2. It's 6, n equals 2, it's 10, right? So it's just going down this. This is how you could predict it. I think this is easier to remember, but if you like memorizing equations, this doesn't matter. So like that. So just so that you know. Now, it becomes a little bit complicated, okay, if you have rings that are fused. Okay, so if they're fused like this, where they're only connected through one carbon, okay, what's happening is you have two separate aromatic systems. Okay, they know about each other. They're sort of waving. But if they're connected with between two carbons, two or more carbons, okay, so that they're aligned like this, then the whole system is going to be aromatic. And there's some really complicated rules to figure out is it aromatic or not. But 98 times out of 100, if you have a fused ring if a fused ring like this, it's going to be aromatic. Okay, stuff like that. And so, if on a test you see that, pretty good shot of saying that that's going to be aromatic, assuming that everybody has a P orbital. Okay. Now, heterocyclists become a little bit more interesting, okay, because they can have lone pairs. Okay. Now, if a carbon has a lone pair, you have to count it. Okay, as part of that. But lone pairs on heteroatoms, they're going to do whatever they need to do, either add it or not, to make the compound aromatic. Okay, so for here, 2, 4, 6, and if you count the lone pair, that would be 8. But what it does is that the nitrogen comes out here, right? So that would end up being 8, which would be anti-aromatic. But if it just shifts that out of the plane, it's like it's not even there. And so we just have the 2, 4, 6, aromatic. Here, 2, 4, right? But if it puts these lone pairs in the system, well, now it's aromatic. Okay? And then here, with the furan, right, 2, 4, and then what it does is it only puts one set in to make it 6. Therefore, it's aromatic. So with that. And so what they do, so in general, what's going to happen is the heterocycles are going to either add it or not to make it aromatic. Okay? What that really wants to do the heterocycle. If it's on a carbon, you got to count it. If it's a lone pair on a carbon, you got to count it. If it's a double bond on a carbon, you got to count it. But if it's on something else, you may not have to. Okay? So you can get ions. Okay, so for here, aromatic ions, right? So with that, so each one of these carbons here has a p orbital, right? These two are part of double bonds. This one has a lone pair, so that's good. So about that, and so here we go, right? So about that, so. Right? So we have 2, 2, 2. So we have 6, and so this is aromatic. Okay? The other. Oh, by the way you make a 7-member ring is start making an octagon, and then before you do the last one, just connect them. So for this one, it's here, 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 plus charge here. So there's no lone pairs here. Okay, if they were, I would have drawn them. Okay, but it does have a free p orbital, right? Because it's charged. So these are part of double bonds. These two are part of double bonds. These are part of double bonds, right? So 2, 2, 2, 0, right? So 6, aromatic. Okay? Now, but this one here, right? This is on a carbon, so you have to count it. So 2, 2. So this ends up being 4. So that's anti-aromatic. Okay. Same thing with this one. Right? There's no lone pairs here, so it's 2, 2, nothing here. So 4. So this is anti-aromatic. Okay. So here's a question: is it aromatic? Okay. So remember, so the rules are, right, so aromatic, anti. Right, so you can start at 6, right? So 8, 10, 12, 14, 16, 18, 20, and so on. You can also go backwards, right? So 4, 2, right? So it's going to be 2, 4, 6, 8, 10. Start bouncing back and forth. Like that. Now, for this one, Okay, now every carbon here is part of a double bond. Okay, here, here, here. Okay, so let's start counting. Right? 2, 4, 6, 8, 10, 12. So that's over here, so this is going to be 8. Okay. So for this one, right, the sulfur has 2 sets of lone pairs, right? So 2, so 2, 4, right? And then it's right here. So really all we want to do is add 2 more. So let's just take one of these to make a 6. We're just not going to worry about that one. So this is going to be aromatic. Okay. It's not a carbon, so we can get away with not putting it in. Okay. Now for this one here, right? So this right here, right? It's these 2 carbons are part of a double bond. This one has a charge, so it's okay. So everything has available p orbital, right? And it only has these 2 pi electrons, right? So there's no double bond up here. So yeah, so that's aromatic. 2's fine. Okay. So start making your 7-membered ring. So start making your octagon, and when you get to this point, go like that. There you go. So there. Okay. Now, pi bond, pi bond, pi bond. Here's a CH2. So this one, it doesn't have a charge. It doesn't have it's not part of a pi bond. It doesn't have lone pairs. Okay, and you have to be able to do that all the way around the ring. Okay, if you can't, then it becomes non-aromatic. Like that. Okay, because there's a break. Okay, and if you want to start double, single, double, single, double, and then no. So like that, and then it's going to bonk into that, not be able to go further. Now, so like that. So now for these, you don't have to memorize these. It's just showing you that these aromatic compounds are incredibly important in biochemistry, right? So these are all different. Amino acids, right? Phenylalanine, tyrosine, tryptophan, right? It's got this indole ring here, so like that. So as well as the purines and pyrimidines from DNA. So you can also see this. It's a little harder to see, but you have this nice aromatic ring in the heme system and then chlorophyll. Now what's interesting is if you look at heme versus chlorophyll, they're really, really similar. Okay? And so, no one of them's doing manganese, one's iron, or magnesium versus iron, but that's okay. But notice how a lot of the structure is the same. All we're missing is, double bond, single bond here. Here, what's happening is these 3 carbons here are actually those 3 carbons there. Okay, you've oxidized. So these 3 here are here, here, and here. And so what's happened is this has been oxidized and then attached over here. So this is slightly different, but it's not that far away. And then here, this right here is just extending away from here. So the molecules themselves, this is in plants, this is in, in animals, right? Most animals, stuff like that. And so, certainly different, but very, very similar. Okay, this is aniline, right? So 2, 4, 6, 8, 10, right? So it's not aromatic, but or 10 aniline versus 18 aniline, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, right? So 18. This is aromatic. Okay. There you go.